So a little more background about me. My last name is Ciuffo. It's a weird spelling, I know. You might know me online as Ciuff. Anybody? Ciuff Tech? I'm the guy who made that receipt printer camera that could take pictures. No? Anybody? OK, online fame. Anyway, yes, thank you, and welcome to Assessing Critical Trade-Offs During VR Hardware Development. My day job is at Synapse Product Development. We are a multidisciplinary engineering design consulting firm based out of Seattle, Washington, focusing mostly on consumer electronics. We have offices in Seattle, San Francisco, and Orlando. And our parent company, Cambridge Consultants, extends that reach all over the globe and into other markets such as industrial and scientific markets. Also based out of Washington, right across the water, is Valve Software. Most of you, I hope, have heard of Valve, famous for the Steam games platform and a lot of great titles, Half-Life and whatnot. Back in 2014, they approached us to help them develop a virtual reality technology, which came to be known as Steam VR. I entered the project about 2 years ago in the spring of 2016, helping to develop their hardware developer kit. Valve's idea was that anybody who wanted to make VR hardware work with Steam VR could. So we developed a hardware kit, developer kit, some documentation to go with that, and even offered courses at the Synapse office in Seattle, where developers could come in. It was a 2.5-day course where they learned how to make their hardware function with the tracking system. This 2.5-day course has been boiled down to a really fast 20-minute session for today, so I hope I don't talk too fast, but we got quite a few things to cover. So here are the 3 main pitfalls we're going to cover, and I'll go into detail on these in a bit, but the general concept is you really want to design a device that's going to work with Steam VR to be a VR device from the start. It's not the kind of thing you can really tack on the end. A lot of people want to take something they've already built, whether it's a pair of augmented glasses that needs some kind of precise tracking or some kind of controller they made, and they want to add Steam VR tracking to it to take advantage of that really precise system. It's difficult to do, and we'll explain why throughout the deck here. Anybody? OK. So the typical hardware development process works as follows. You start out with your concept, and you have a 3D model of what you want. And you want to make sure it's going to operate well inside a Steam VR play space. So there are some software tools you can use to simulate the behavior of the device and how well it will work and how precisely you can track its location and orientation. Once you're happy with that simulation, you can move on to a prototype phase. This is a 3D printed model of the HDK we made at Synapse. And you can see a bunch of circuit boards literally just hot glued in there and wired up by hand to test performance. Obviously not something very manufacturable, but it's really good for validating that your design works in the real world and takes into account all those human factors you might not expect in a simulation. And then finally, when you're happy with that, you move on to a final version. This is a injection molded model with custom flexible circuit boards and all that, so highly manufacturable, much cheaper than other ones. In the interest of time, we're going to focus entirely on the simulation phase. So what do I mean by simulation? Like I said, there's a whole hardware developer kit created for Steam VR, and part of that is a software suite, including some simulation tools and a ton of documentation that covers everything I'm going to talk about today and a lot more. If you want to be a part of this and try it out yourself, all you need to do is sign up to be a partner with the VR licensing program through Valve, and you can download the hardware developer kit suite just like a game. It actually comes through the Steam platform. You'll note I've very cleverly hidden my Steam ID because I created it when I was 14 years old, and I'm not super proud of it, so I won't share it with you guys. Moving on. So VR hardware is difficult to tack on to an existing design. And again, what I mean is a lot of people just want to say, oh, I'll just add some components to a circuit board, add a few sensors, and it'll make it work. And that's very difficult. There's been a couple different attempts to do that. Probably the most notable would be the universal tracking puck from HTC. This is basically a Vive controller with the handle cut off. It has no buttons or anything, but it's meant to be stuck onto an existing design to allow it to track and get that precise location information through Steam VR. It's a really good product when used correctly, but it's difficult to use well, and depending on your application, it might not be much use to you at all. And again, the talk's not supposed to focus entirely on this puck, but it sort of represents the idea of having an isolated, small portion of a design you can tack on to something that already exists. And we're going to say why that's difficult to do. So let's drop this puck into the design software. So this is part of the software suite, H&B Designer, and it gives you sort of a visual representation of how well the device will work in Steam VR. So what we're looking at here is the puck from the point of view of a base station. If you used an HTC Vive before or any Steam VR product, you know that there are 2 base stations in the room that aim in towards the play space. Only one of those is actually necessary. The second one kind of offers as a backup because you have to maintain a line of sight with infrared light from the base station to your device. And if you turn away from one base station, the other has to take over. So here we're looking from the perspective of a single base station, and you'll see we have all these little white dots which represent optical sensors that the base station can see, or that rather can see the base station. There's a lot of nuance to how to design a device to work with SteamVR, but the general rule is you have to have at least 4 sensors with a line of sight view of a base station at any given time, and one of those 4 sensors has to be outside the plane of the other 3. If all 4 sensors are on the same plane, your device will not track well. And as you can see here, we have like 5 or 6 sensors visible. They're all at different depths, so you end up with a blue color on this map here in the center. So that indicates the device will track well when viewed from this angle. If I had the software out, I could rotate this around and show you all the different angles, but in the interest of keeping this a slideshow, you can also do this view, which is basically if the previous map were a globe, or the previous slide were a globe, this slide would be that globe stretched out into a 2D map. So here we're looking at angles of view, yaw and pitch angles, viewing the device from the perspective of the base station. And these are 4 different criteria you can use to evaluate tracking. Boiling it down to the simplest form, the darker the blue, the better. The more red you have, the worse off you are. So a well-designed device will have as little red as possible. And with the Vive Tracker Puck, as expected, you see these kind of red zones to the left and right of each frame. That represents the bottom of the puck, which is meant to be mounted onto a device, so there are no sensors down there, so obviously it won't track very well when viewed from the bottom. But that's considered to be generally acceptable. We just want to keep that red as small as we can. One thing as an aside I found kind of interesting when I was making this slideshow is these little red darts down here, which are odd because the device is largely symmetrical, and that kind of represents an asymmetrical element. And I was looking into it, it should be a triangle, relatively symmetrical triangle shape, yet those darts sort of stick out. And the reason for that is the USB port. So when HTC wanted to add the USB port to this side, they had to change their sensor placement from what the other sides had, and that made the tracking slightly worse. These sensors are all kind of in a plane, so the device won't track super well from that angle. And that's a really great example, sort of right off the bat, of how you have to compromise between the VR requirements of your device and the other requirements, the UI elements, USB ports, that kind of stuff. Again, the software is a worst case scenario sort of estimation, so realistically, that won't have any appreciable impact on performance, but it's something you want to make sure you keep in check while you're designing your devices. So let's do a case study. This is a model I just downloaded off Thingiverse and blew up to the size of approximately the size of a human. And this guy is holding some kind of blaster controller, let's say, we've developed, and we want to add SteamVR tracking to it. So let's see what that's going to take. Attempt number 1, we're going to add our VR tracking portion somewhere in the middle of the device. This could possibly keep costs down because the trigger and a lot of the UI, UX elements are going to be somewhere in the center of the blaster, which means that the barrel, the barrel and the stock will be just empty plastic, keeps costs down. It'd be great. Let's see how well this tracks. Not so great. So the small red zones have ballooned up, and that's a result of the soldier and actually the blaster itself occluding light coming from the base station. So for a large swath of angles, we're not going to get any line of sight to our base station. You can actually sort of make out the head and shoulder of the soldier and even the tip of the blaster right here in these maps. So you can see it's kind of casting a shadow on the resulting data. So how do we fix this? Well, one thing you can take advantage of is the fact that these maps represent not really area, but angles. So it's angles coming out of the device. So that red spot on the map actually represents kind of a cone extending from the bottom of the tracking puck. And the farther you get away from the puck, the larger your obstruction can be without having any real impact. So if we want to fix this problem, let's try to move the puck farther away from obstructions and see if that improves performance. Let's place it right on the tip of the blaster. It looks kind of goofy, but it could work. So let's see what happens. As you can see here, we still have the red zone, but it's much smaller. It still has kind of the outline of the soldier here. It's a lot smaller and confined, and in fact, in a lot of areas, the original lines from the tracker puck alone are sort of bleeding out past the soldier, so we're not actually degrading tracking performance much at all, which is great. And you can see the comparison here going from that small change has reduced that red zone a lot and will increase how well this device performs in SteamVR. But there's a problem with this approach, and that is that SteamVR, like any outside-in, or really any optical-based system, has a limited frame rate, whether it's the frame rate of a camera, or in this case, the rate at which the lasers inside the base stations can spin. It's a 60 hertz frame rate, which seems kind of fast, but when you realize you have very fast motions in gameplay, you're only going to get an absolute update of location at fairly distant intervals. So you have to fill the gaps of something. And that's where your IMU comes in. So your inertial measurement unit, in this case it's from InventSense, the MPU 6500, is an accelerometer and gyroscope combination. And by doing some simple calculus, I say that, I didn't write the software, simple calculus and adding up all those accelerations over time, you can fill the gaps between the optical samples and get a really smooth motion. And this is great because you can get an IMU that goes up to 1,000 hertz fairly easily without having to increase the cost substantially as you would if you wanted to increase the speed of the lasers or the frame rate of a camera. But there's an issue with that, and it boils down to high school physics. So if we place our tracking puck on the tip of our device and place it far away from the user, any rotation of the device is going to amplify the acceleration that the tracking puck experiences. So if we imagine our IMU is out here in the end, and the user goes from a patrol ready to a firing pose pretty quickly, over 200 milliseconds, that's like a fifth of a second, not super fast, it's not superhuman or anything. The minimum acceleration that IMU will experience is 5.1 Gs, which G is like G-forces in a roller coaster, that's what we're measuring here, that's the minimum, and that's assuming it's a smooth motion and not jerky at all, and there's no start or stop or anything like that. So realistically, it'd be a lot higher than 5.1. And this becomes a problem because the IMU we're using is limited to plus or minus 8 Gs in the mode we're using. So you could change the mode. You can go from plus or minus 8 Gs to plus or minus 16 Gs and allow a much wider scale of measurement so you don't end up clipping the end of your scale and going off the end. But the problem is when you double the scale, you have the resolution. It's like blowing up an image and printing it out. You end up with larger pixels, less granularity, and as a result, you have more error in your measurement and your tracking performance will go down. So how do we address this problem? There are two options. One is you can move the IMU somewhere else, and the other one is you can find a different IMU. So let's try option the first. Well, if we move the IMU or the device closer to the center of our object where there's less extreme rotations, our minimum G-force goes from 5.1 down to 1.8 Gs. So substantially less, but we've already tried this before, and we know that this device will not track well due to the obstructions of the blaster and of the user. So let's try buying a different IMU. I went online, looked around, found a part from Analog Devices, the ADXL357. It has a similar voltage requirement, sort of similar size. It's small enough to fit in a consumer device. Much higher scale, much higher resolution, much higher cost. It's about $46 higher cost than the IMU we're currently using. So you could do this, it would work, but you're going to end up paying a lot more. So if you try to tack on VR and you don't really integrate it into the device, you can make it work, but it's going to end up costing you more in the long run, and any attempts to do that to save cost will probably end up being fruitless. So what's the right way to do it? Well, you want to integrate your VR tracking into your device. In this case, that means placing sensors all around the device. Here we have the blaster, and I just dropped it into HMD Designer, which has an option to just auto-place sensors throughout. It's an okay tool. It doesn't do a perfect job. You can always do better when doing it by hand, but it gets you about 80% of the way there, and it gives you a good feel for how well your device will work. So I just had to pepper a few sensors around the device, and unfortunately, from behind, we have a large red zone. And it's odd because you see we have like 1, 2, 3, 4, 5, maybe 5 or 6 sensors visible from that side. The problem is they are all on the same plane. And as you said, when you have coplanar sensors, you're going to have degraded tracking performance. And unfortunately, even if you go in there manually and try to move some sensors around, you're not going to improve the performance at all because the entire side of your industrial design is a flat surface. And this is a really common problem because us electrical engineers like making really flat objects. They're super easy to make. And so when you want to make something not flat, it becomes a challenge. So how do we fix this? Well, we have to break up the industrial design somehow and modify it. Here, I just threw some random cubes on there all throughout to break up the surface, dropped it in the same software, and it looks like it picked up a few of the cubes and decided to use them to place sensors and hopefully improve performance. And sure enough, it did. When viewed from behind, that red zone goes away because we have sensors that are now on the flat surface, closer to the base station, farther away from the base station. We get that depth, which enables good VR tracking. So if you want to make your device work in SteamVR, you're going to have to change the industrial design. You don't want to have something that's fully baked and you've already got your marketing materials ready and you're like, all right, let's just slap this thing on there and call it a day. That's just one example of changing the geometry. There's also material limitations of what you can use. Optical sensors have rules about what you can place over them to protect them, and that limits your color options. There's a lot of ways in which you have to sort of start early and integrate these concepts into your design rather than just tacking it on at the end. But if you do it right, you end up with a pretty good product. So this is our best attempt with the puck at the tip of the barrel. whereas this is the same thing with the sensors throughout our sort of cubified blaster. And you'll see that in addition to being able to place the IMU wherever you like, because you've integrated into the whole product, you also actually have slightly better tracking performance. So the red zones are a little bit smaller down here than they are up here. So overall, better product. So some tips. Acquaint your design team early with VR design concepts. What's kind of neat is if you give them those criteria early on, they can use that to sort of drive their innovation and end up with some really cool looking products, which I always find in the VR world kind of funny because, of course, when you're using a controller, you can't actually see it, so who really cares what it looks like? But I'm told that the marketing guys want something pretty to throw in a box, so it has to look pretty neat. And then allow your mechanical and your electrical teams to work together. It's a product where, a kind of field where Synapse, I think, does really well. We have our different engineering disciplines meshed and working really closely together because you can't really have the mechanical team build a box and have the electrical team build a circuit board and slap the two together and call it a day. You really have to think about where you're placing your electronics in order for your device to be manufacturable and cost not too much. And then finally, simulate often and prototype early. And how do you do that? Well, if you're interested in simulating, you can go to this URL down here and get a copy of the SteamVR HDK. It's free to download. You can actually do it right now and, like, on your flight home, start mocking up some 3D models for your next great product and see how well it tracks in VR. Once you're happy with that, you can prototype it out. We always recommend people take advantage of 3D printing and a lot of low-cost, high-speed prototyping technologies to mock it up. For the hardware, all the hardware design files are included in the HDK, but if you don't feel like spinning up your own fab, you can purchase a version of the HDK from Triad Semi. And it's actually a really nice kit. It even comes with all the wiring you need. One of the students that came to Seattle was able to, in about 4 hours, take this HDK and turn a Nerf gun into a VR tracking Nerf gun. And they even wrote a game in Unity for it. Like, it was pretty amazing, actually. But it's super easy to use and really easy to get involved in. And then once you've made your prototype and you're really happy with it and you want to bring it to market, and you have any trouble, feel free to reach out to Synapse. We do VR consulting all the time, have a lot of experience in this, and we'd be happy to help you bring your product to reality. Any questions? Nope? Okay, well, that's all I had. Thank you.